Hey, what's going on, guys? Maksymkorzh here. So the last video, me and my dad recovered my very first computer, ZX Spectrum, 30 years old, homemade machine. And I was so excited about that I decided to try to write an emulator for that machine. Well, not from scratch. I'm using the existing Z80 CPU emulator, and obviously I'm using the existing ROM. And now I'm trying to bind things together, mostly in order to actually learn about the target architecture, because I think that that the matter of writing an emulator is what's the most benefit of that is that actually that's probably the best way, practical trial and error way to learn about the target platform. Well, that's for me personally. So here's what I currently have. FPS is miserable, and come later up exactly. So here I'm just reloading the machine and having this label down below. So actually, now at the moment, the ZX Spectrum ROM is running in a loop, and if only I had a keyboard support here, which I didn't yet implement, it would then allow me to type some basic code and actually work with the machine. So what I did so far, I just so yeah, like for those interested potentially in creating their own emulators, this might be quite a useful thing. So first, I kickstarted with downloading this quite nice CPU from GitHub, Dr. Goldfire. Okay, so this is the CPU, and it asks you to define 4 functions. So read in memory, write in memory, read in IO, and write into IO. So I did that as the documentation asked me to. So if I go to init.js, so here I have this read into memory, write into memory, write into memory. This line is allowing to write to the ROM part, so the first 16K, where the ROM itself is available. I don't actually think that the ROM itself would be trying to write bytes where it exists on its own, but anyways, for user later on, this restriction might be on the cards. And since I'm not sure what this IO read and write do, like what kind of port and value are we talking about, I just left them as a placeholder just to make sure that works. And then I'm creating the CPU instance here. And another thing, so I just created a memory here, so 64K of RAM. I know that ZX Spectrum has only 48, that's the one I'm emulating, but for now we just have the 64. And anyways, the memory test runs through all of this. It tries to run through all of this 64. All of the 64K K of bytes. So what I do here, when I imported the ROM, so here is the ROM, by the way. It's original ROM for 64 for 48K ZX Spectrum ROM. So here it is. So I just put these values to memory in this single line of code here. So by this time, what we have like the ROM being kind of written into the memory, and then the main loop goes here. So the CPU instance has already been created in the init. Here the CPU instance has been created, or probably even better to put this to the main, because this is just the initialization part to make the CPU working. So it's probably better to just put it right here. And then once the window is loaded, the CPU loop is called. So I'm calculating the FPS here, this lines and this line, just to calculate the FPS. And the loop itself, so currently it's 100 thousandths of cycles. I update the screen and call this function kind of in the background. So by changing this number, we can measure the speed of the emulation. I'll now demonstrate you this. But at the core, what we got here, we're just asking the CPU to run the next instruction. And in Z80, the program counter on load, it points to address 0, and whatever it encounters there, it just starts executing. So, for instance, if I just upload, it starts executing the ROM, which brings us here. So if I do this a little bit slower, like this, for instance, then all the stripes that are walking across the screen, it's actually the matter of testing the all of the memory, not only the video memory, but when the video memory is getting ingested, it also kind of, it's about that, you know. And then this label, which means that we're in there. So yeah, a proof of concept is here. Yeah, if only I could type something that, yeah, probably just jumping straight into the basic loop and trying to execute something, and I don't yet interpret this attributes, color attributes. So it's just the bitmap for now, just black and white, no color attributes at the moment. But what makes me really concerned in this is this miserable FPS. So I have no idea how to fix this at the moment. However, I can show you how this why actually this is happening. So we go to the display, the part that I've spent the most time writing. So it starts from, so here I have the function to fill the memory, just to make sure that it covers everything properly. So render pixel as the tiniest building block. So the pixel here is 3 actual actual screen pixels. So 3 actual screen pixels, 3 by 3. Like it's 9. Yeah, 3 by 3. It's 9. So it takes 9 pixels, 9 screen pixels to draw 1 emulated pixel. So this is the pixel size here. Then render byte. So the way how the memory is organized is quite interesting, and I'll probably show you this using the existing emulator. But for now, so written pixel just like render pixel just draws a single rectangular shape on a screen at the desired x and y coordinates. So there are, in terms of pixels, there are 200s. I forgot how many. So let me quickly. Let's open terminal, view folder. In the resources, video memory PNG. 256 pixels wide and 192 height, 256 width. But interestingly, that these bigger cells are 8 by 8. It's called characters. Apparently, it's the better way. But it's really tricky how this actually gets rendered. This is really tricky, and it's the most time and effort spent trying to understand how this actually working. So it's not linear. It's not like so we have the memory range from 4000s to 57FF. So this leftmost pixel is I'm sorry, not the pixel actually, but so if I just make it like this. It is really interesting. So like 1, 2, 3, 4, 5, 6, 7, 8. So this 8 pixels is the single byte. So let's say 4000 hexadecimal is this little stripe, then 4001 is this little stripe, then 4002 is this one, and we go until the very last part. However, here we have 401F, and then where would you think the 4020 starts? I was thinking naively that it goes here, but no. 4020 goes actually here. Then 4021, 4022, 4023, and so on. So it prints like this line, then this line, then this line, this line, this line, and up to 8 lines. And then it starts picking drawing the second line, and then the third one. So that's how the mapping works. And just to demonstrate you that visually, let me open the Fuse emulator. And if we write a simple program here, like for instance, Dan, poke, and let me just recall my range, just very quickly. So from 4000, nope, hex, 4000, go into decimal, 16348, 16348, comma, and 255. So just be all the bits within the byte. Oh no, I need to do this in a for loop, obviously. So for n equals to, oh, did I close my calculator? Nope. 16384, 2 and 2, let's go into hex, 57FF, yes, 57FF, decimal 22527, 22527. Here I want to poke n, so that current address with the value 255, and 30 next n. Okay, and now let's run this. And this is the order of how the screen bytes are actually being mapped. So so it just goes like this tiny byte by byte, formulating the line. And there are three areas. So the first 64 lines, then it goes for the second 64 lines, and then finally it goes for the third 64 lines. And it really took me kind of a long time to figure this out. Basically, this wasn't really trivial. So this is a very interesting mapping, and I've been reading like why exactly they did it like so. So for performance reasons mainly. But anyways, that's how it works, and eventually just draws all of the screen. So yeah, so this mapping actually gives us an idea, like you want to draw something in a certain area of the screen, using the bare like poke commands or machine codes. Then we need to make sure that we calculate all the offsets properly. But anyways, so once I managed to actually make this behavior, kind of mimic this behavior, it's, yes, one exit. It actually, after this, I saw this line down below finally, because before that it was just some gibberish on the screen that kind of looked like the QR code of some sort. Yeah, it was really fun. So next challenge is actually try to make the FPS being a bit better, because I'm not sure why it drops. Well, actually it's clear why it drops so significantly, but I'm not really sure how to help this. But anyways, the current logic I have at least ensures the fact that I actually do understand how the memory video is mapped. I do properly understand how the video memory is mapped, which is already good news. So if I make any progress on this project, I would be happy to share this with you guys as well. So this is it from my side. Thanks for watching. Until the next time, and take care.